Hey there, space cadets. Have you ever thought about what's protecting us from all the crazy stuff happening out in deep space? Well, picture this. A giant bubble, way bigger than you can imagine, shielding our entire solar system.
That's the heliosphere.
Right. And today we're diving deep into some research about it. We'll cover what it is, why it matters, and a big mystery surrounding its shape.
Buckle up.
So to kick things off, can you give us a quick rundown of what the heliosphere actually is?
It's fascinating, really. This protective bubble, the heliosphere, is formed by the sun's solar wind, which it's a constant stream of charged particles blasting out from the sun, pushing against the material floating between the stars. It creates a sort of shield.
Okay, so the sun is constantly blowing this bubble of charged particles around our solar system.
Yeah, exactly.
And that protects us from the stuff out there in interstellar space.
Yeah, it does.
I remember reading about cosmic rays, those tiny bullets of radiation that can really mess things up. The heliosphere helps protect us from that, right?
It does. Think of cosmic rays, like tiny bullets of radiation zipping around the galaxy.
Oh, wow.
They come from exploded stars, and they can do some real damage to living things and even mess up our electronics. The heliosphere is our first line of defense. It blocks most of those cosmic rays from hitting us.
So it's like our own personal force field against all that interstellar radiation. That's pretty amazing. But I heard that scientists aren't actually sure about the shape of this heliosphere.
And here's the kicker. Scientists still aren't totally sure what shape it is.
Oh, really?
We have all these models, spherical, comet-like, even something like a croissant.
A croissant.
But to truly crack this mystery, we need to look at what we've learned from the only spacecraft to actually cross the boundary of the heliosphere, that outer edge called the heliopause.
You're talking about the Voyager probes.
I'm talking about the Voyager probes, of course.
Oh, yeah, Voyager. Those things have been traveling for, what, like almost 50 years.
Launched way back in 1977, and they're still out there sending back data from beyond the heliosphere. Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2010. It was a huge deal for space exploration.
Yeah, it was major news. It's incredible that those probes are still sending back information after all this time, but I guess they weren't really designed to study the heliosphere in detail, were they?
Absolutely groundbreaking.
Right.
But there's a catch. Voyager, as amazing as it is, wasn't built for this. For example, Voyager's cosmic ray detector, designed in the 70s, has a limited energy range. So we might be missing data on the really high-energy particles, the ones most crucial to understanding the heliopause and what's beyond it.
So we've got these amazing probes that have crossed this boundary, but they can only tell us so much.
Precisely.
I guess that means we need a new mission to really understand the heliosphere, especially its shape.
Exactly. We need a purpose-built interstellar probe equipped with all the latest technology. Imagine this. It would be able to measure things like plasma density, map magnetic fields, even take pictures of the heliosphere from the outside. Stuff Voyager could only dream of.
Okay, that does sound pretty incredible. It would be like sending a high-tech photographer out to the edge of our solar system.
Exactly.
But space is big, really big. How long would it take to actually get a probe out there?
Yeah.
To the heliosphere's edge?
Even with a speed boost from Jupiter's gravity, we're talking at least 50 years.
50 years. Wow. Okay, so while we wait for a new probe to be built and launched, which is obviously quite a while, why don't we dive into the current research on the heliosphere's shape? We'll explore those different models, from spheres to croissants, and try to figure out what the evidence is pointing to so far.
Let's do it.
All right, stay tuned as we unravel the mystery of the heliosphere's shape.
Well, one idea is to map the heliopause using the density of plasma.
Mapping the heliopause with plasma density. That sounds a bit tricky. It's like trying to find the edge of a cloud, isn't it?
It's tricky for sure, but not impossible.
So how would a probe actually do that? I mean, how do you measure the density of something that's essentially invisible?
Well, a probe could take continuous measurements of the plasma density around it. As it gets closer to the heliopause, that boundary between the sun's influence and interstellar space, we'd expect to see a significant drop in plasma density. That would be our signal.
Ah, so it's like using a depth finder to map the bottom of a lake, but instead of depth, we're looking at how dense the plasma is.
Yeah, that's a good analogy.
That makes sense. But isn't there more to the heliosphere than just plasma? I mean, you mentioned magnetic fields earlier. Do those play a role in shaping the heliosphere too?
You're right. Magnetic fields are key players in this cosmic dance.
Oh.
The heliosphere isn't just shaped by the solar wind pushing outward. The interstellar medium with its own magnetic fields pushes back. A new probe would need to measure the strength and direction of these magnetic fields, both inside and outside the heliosphere.
Okay, so we've got these two forces. The sun's magnetic field and the interstellar magnetic field, kind of like having a tug of war. Whoever's stronger in a certain spot dictates what that part of the heliosphere looks like.
That's a pretty good way to visualize it.
And I remember you talking about magnetic reconnection earlier, those snapping magnetic field lines. Doesn't that make things even more complicated?
You got it. And remember that magnetic reconnection we talked about, those snapping magnetic field lines? Well, that adds another layer of complexity to the picture. It means the interaction between those magnetic fields is dynamic and unpredictable, constantly changing the shape of the heliosphere.
Wow, this is getting complex. So we've got these pieces of information, the plasma density, the magnetic fields, this chaotic magnetic reconnection, and somehow we need to put it all together to get a clear picture of the heliosphere.
Exactly. And it's a puzzle worth solving, not just to satisfy our scientific curiosity, but because it has practical implications for life here on Earth.
Oh, right. We talked earlier about how the heliosphere protects us from cosmic rays, so if its shape is constantly changing, I guess that means our level of protection could change too.
It's a possibility. We know that the heliosphere isn't static. It expands and contracts in response to changes in the solar wind and the interstellar medium.
So if the sun, let's say, entered a region of space with a lot more interstellar material, would the heliosphere shrink? Would we be less protected?
That's a very likely scenario. If the interstellar pressure increases, the heliosphere would likely contract. And a smaller heliosphere means less protection from those harmful cosmic rays.
Okay, that's kind of unsettling. Is there any way to predict these changes, like a cosmic weather forecast or something?
That's one of the biggest reasons why this new interstellar probe is so important. By taking continuous measurements of the heliosphere over decades, it would essentially create a long-term weather report for our solar system.
Oh, I see. So it wouldn't just be about mapping the heliosphere at one point in time. We'd be able to track how it evolves over time, like how it breathes and reacts to its surroundings.
Exactly.
And that would give us a better understanding of how those changes could impact us here on Earth.
Precisely. We could learn to predict when the heliosphere might weaken, giving us time to prepare for things like increased radiation exposure for astronauts and satellites. It could revolutionize our understanding of space weather.
Okay, now I'm really starting to see why this mission is so important. But let's be realistic. We're talking about a probe that would take at least 50 years to get out there. It would have to be, incredibly resilient to survive that journey and operate for decades in the harsh environment of interstellar space. I mean, is that even possible with today's technology?
It's definitely a massive engineering challenge, but not an insurmountable one. We've already seen the incredible longevity of the Voyager probes, which are still going strong after almost 50 years in space.
Yeah, that's true. I guess an interstellar probe would be built to last even longer. I mean, imagine all that time and money invested only for the probe to stop working after a few years. That would be, well, heartbreaking.
Precisely. Redundancy in cutting-edge materials would be essential to ensuring the probe can operate for decades, potentially even centuries, in that unforgiving environment.
Okay, so assuming we can build a probe tough enough for the job, is there anything else that makes studying the heliosphere particularly challenging? I mean, we've talked about its size, its shape, the magnetic fields, the plasma. Is there anything I'm missing?
Well, we've been focusing a lot on the shape and behavior of the heliosphere. But there's another crucial piece to this puzzle. Its composition. What is this bubble actually made of? And how does that composition affect its interactions with the interstellar medium?
Ah, right. I admit, I hadn't really thought about the specific ingredients of the heliosphere. What exactly is out there between the stars? I mean, I know it's not just empty space.
The interstellar medium, which surrounds the heliosphere, is a fascinating mix of gas, dust, and cosmic rays. It's incredibly dilute, almost a vacuum compared to the environments we're used to, but it's not empty.
And this interstellar medium is what's constantly pushing against the heliosphere, trying to get in.
Right, exactly.
So the heliosphere is like a giant filter, protecting us from all the bad stuff that's floating around out there.
That's a great way to put it. It's like a giant cosmic air purifier, scrubbing out the worst of what interstellar space has to offer. But it's not a perfect filter. Some interstellar particles, especially those that are electrically neutral, can slip through the heliosphere's defenses.
So even with the heliosphere, we're not completely isolated from interstellar space. There's always some exchange happening, some give and take.
Yes, precisely. There's this constant back and forth, a tug of war between the solar wind pushing outward and the interstellar medium pushing inward. And the heliosphere is the battleground, constantly shifting and evolving as these forces interact.
Wow, it really makes you appreciate the complexity of our solar system. So to understand this cosmic battle, we need to know what these forces are made of, right?
Exactly.
Like what kind of gas and dust make up the interstellar medium? What are the properties of the interstellar magnetic field?
All those things. And those are all questions that an interstellar probe could help us answer.
This has been incredible. I'm starting to see the heliosphere in a whole new light. It's not just a static bubble, but a dynamic, breathing shield, constantly interacting with its surroundings. And by studying it, we're not just learning about a distant object, we're learning about the very forces that shape our cosmic neighborhood.
Exactly. It really highlights the interconnectedness of everything in space, doesn't it? What happens billions of miles away in the interstellar medium can have repercussions here on Earth. It all comes back to the heliosphere and its role as our cosmic protector.
Yeah, it's amazing to think that something so vast, so seemingly distant, can have such a huge impact on our little corner of the universe.
It really does highlight the interconnectedness of everything in space.
Right.
What happens billions of miles away in the interstellar medium can have repercussions here on Earth. It all comes back to the heliosphere and its role as our cosmic protector.
It really makes you realize how much we still don't know about our own solar system. I mean, we've been exploring space for decades, but the heliosphere, our cosmic home, is still shrouded in mystery.
True, and the more we learn about it, the more questions we seem to uncover. But that's what makes science so exciting. Each discovery opens up new avenues of exploration, pushing us to delve deeper into the unknown.
Okay, so let's say we launch this incredible interstellar probe. We wait patiently for 50 years. It reaches the heliopause, starts taking measurements, sending back all this data. What are we hoping to find? What are the big questions about the heliosphere that we're most eager to answer?
Well, one of the biggest mysteries is how the heliosphere changes over time. We know it's not a static structure. It expands and contracts, it ripples and vibrates in response to changes in the solar wind and the interstellar medium. But we don't fully understand the patterns of those changes or what drives them.
So it's like trying to predict the weather, but on a cosmic scale.
Exactly.
We know the heliosphere has its own kind of storms and shifts, but we don't have a good forecast yet.
Exactly. A long-term study of the heliosphere, the kind of data we could get from a dedicated probe, would be like having a historical record of its weather patterns. We could start to see how it's responded to different events, like changes in the sun's activity or encounters with dense interstellar clouds.
And that could help us predict how it might behave in the future.
That's the hope.
Potentially give us a heads up if we're heading for a rough patch, cosmically speaking.
The more we understand the heliosphere's past, the better we can predict its future. And that knowledge could be crucial for protecting our planet and our technology from the hazards of space.
You're talking about things like solar storms and cosmic rays, right?
Exactly.
The stuff that can disrupt satellites, mess with power grids, even pose a risk to astronauts.
Exactly. The heliosphere is our shield against those threats. But a shield is only effective if you know how it works, how strong it is, where its weak points are. And that's what we're trying to figure out.
It's like we've been living in a house with a roof over our heads, but we've never really inspected the roof, never checked for leaks or potential weaknesses. Now with this interstellar probe, we're finally getting up on a ladder and taking a closer look.
A very apt analogy. And what we find during that inspection could have major implications for the future of space exploration and even life on Earth.
Wow, this has been an eye-opening deep dive. I had no idea how much was going on at the edge of our solar system or how crucial the heliosphere is to our existence. It's made me realize that space exploration isn't just about discovering new worlds. It's about understanding our own place in the cosmos, our cosmic home.
And that understanding, that drive to explore and learn, is what propels us forward as a species.
Yeah.
It's what leads to new discoveries, new technologies, and ultimately a deeper appreciation for the interconnectedness of everything in the universe.
Well said. So, for our listeners who are now as fascinated by the heliosphere as we are, what's the one thing you'd want them to take away from this conversation?
I'd say this. The heliosphere is a dynamic, ever-changing shield that protects us from the hazards of interstellar space. It's shaped by a complex interplay of forces, and its behavior can have a profound impact on our planet. By studying the heliosphere, we're not just satisfying our scientific curiosity, we're gaining knowledge that could safeguard our future.
Beautifully put. And as we wrap up this deep dive, we encourage you to keep exploring. Read more about the heliosphere, check out the latest news on the Interstellar probe mission, and let your imagination wander to the edge of our solar system and beyond. Who knows what other mysteries await us out there in the vastness of space? Until next time, keep looking up.